Hi guys. So we need to talk about chemical reactions, chemical equations, chemical equations, and the law of conservation of mass. So let's start out by getting your notebook set up properly. So I want you to find a new blank page and write this at the top of it. This should also go into your table of contents. Hopefully you've been taking care of your table of contents and making sure it stays updated. So chemical equations and the law of conservation of mass. I use the little and symbol if you just want to write and, whatever, I don't really care. So I want to start out by talking about a chemical reaction that probably a lot of us are familiar with and enjoy, and that's baking a cake. So what we want to start off by talking about is, say we want to bake a cake from scratch. What are some ingredients you put in there? Well, usually I get flour, sugar, eggs, maybe milk, or oil, especially if you're making brownies. I think you use oil. People say chocolate, sprinkles, vanilla, baking powder or baking soda or something, I don't know. Yeast, maybe, I don't know. Again, I'm not a baker. And these are all good ingredients. What we want to talk about is just a super simple recipe for a cake, though, and that's what we're going to write down, is a real simple recipe for a cake. So let me show you my notes. So a simple recipe for a cake, just super basic. We're not making it chocolate or vanilla or confetti cake or anything like that. Just flour, sugar, eggs, milk, and butter. Now, if you can't fit all of this onto one line, you can leave a few ingredients out. The main point is that we write it in this format where we have ingredient plus ingredient plus ingredient goes to, so this arrow goes to cake, all right? So write it out like that. If you need to pause the video, go ahead and do that. Now, I want to talk real quick about the importance of the arrow instead of an equal sign, because this kind of looks similar to an equation you might see in math, except you're probably not working with things like this in math. You're probably working with numbers and variables, but we've still got plus signs, which we might see in math, but the arrow is something a little bit different. The arrow tells us that this stuff becomes cake. If this was an arrow, it would say that this stuff is the same thing as cake, and cake is the same thing as all this stuff. This arrow also tells us that this stuff can become cake, but cake cannot become this stuff, right? So I can take all these things, mix them together, put them in the oven, and turn them into cake, right? But if I say I'm going to the grocery store, and on my list is flour and eggs and milk, well, I can't say, well, I know I need these three things, but why don't I just buy a cake and I'll just take it home, and then once I get home, I'll take the cake apart, and then I'll just separate it into the eggs and flour and milk that I need. It doesn't work that way, right? These things can become cake, but you cannot take a cake and turn it back into these other things. So this arrow tells us that these are not equal, like an equal sign would, and it also tells us the direction that the reaction can go. So that's a little bit of a difference and kind of why we have an arrow instead of an equal sign. Next, we need to talk about a little bit of vocabulary. The reactants are what we call anything on the left-hand side of the arrow. I use this little squiggly bracket. You can do whatever you want to indicate that everything on the left-hand side of the arrow are what we call our reactants, and everything over on the right-hand side of the arrow are called our products. In this case, we only have one thing to the right of the arrow. Normally, we would have a couple things, and in this case, we have a lot of products. I'm sorry, we have a lot of reactants and only one product. Normally, you'd have two or three of each, but whatever, that's just what we've got in this one. The other thing I want you to write down is yield arrow. That's really just what we call this arrow. It's not just a normal arrow, it's a yield arrow. It tells us that when we put these things together and do a chemical reaction, it yields the products. So that's why we call it that. Now, a way that I like to tell students to kind of help remember that the reactants are there and the products are there is reactants react to produce products. Reactants goes first, products go second. The reactants do the reacting, the products are what is produced. However you want to say it or think about it, but I would definitely write that down. So what I want to do next, so we talked a little bit about cake, and that's a reaction that we're sort of familiar with, that maybe we've done before. Let's talk about another familiar one that's a little bit more simple. I'm just going to use this dictionary as a stand, and that is a burning candle. Okay. This is, again, probably a reaction that you're familiar with in some way, but this reaction is a much more simple one to actually look at. So the reaction of baking a cake, there's actually all kinds of different chemical reactions going on in there, so it's actually really complicated. But this is a much more simple reaction. So let's talk about this, okay? First off, we need to identify what our reactants are and what our products are. So what goes into the reaction and what comes out. Now, for one, there's a flame, obviously. That flame, if you remember, flame, fire, heat and light produced, that's a sign that a chemical change is happening. What is going into this chemical reaction that is obviously happening because there's a flame? A couple things to think about. When you burn a candle, say you're burning a candle for a couple hours, something goes away, right? The wax itself burns away. In fact, this candle, you can't really see because it's lit right now, but there's kind of a divot in it. You'll notice that with candles, that often the outside edge is taller than what's on the inside by the wick. And that's because that wax has burnt away. So one of our reactants is wax. Okay. Now, there's two reactants here, so we got to figure out what the other reactant is. And a good clue for a lot of students is what happens when I put this over the top of the candle. I'm taking away a really important reactant, and the candle goes out. So I took away, what did I take away? I took away oxygen. The candle needs the reactant of the wax and also oxygen in order to continue burning. Maybe you know that fires need oxygen to burn. They do. So those are our two reactants, wax and oxygen. Okay, now let's talk about our products. We also have two products. Now the products can be a little bit harder to think about with a candle, but let me tell you this. This is usually a good hint. Wax is actually really similar to fat and sugar. Wax is made up of a bunch of carbons and hydrogens. So is fat and sugar, just a bunch of carbons and hydrogens, sometimes a couple oxygens as well. So, since this candle is essentially fat/sugar and oxygen burning, it's the same thing that happens when we breathe. We're burning sugars and fats and inhaling oxygen. This candle is burning wax and also sort of inhaling oxygen. So by breathing, the chemical reaction that happens when we breathe is a very similar reaction to what happens when this candle is burning. So let's think about what we breathe out. We breathe in oxygen, we breathe out carbon dioxide. That's one of the main gases that we breathe out is carbon dioxide. Okay, so that's one of our two reactants. Remember that's one of our two products. One of our products is carbon dioxide. The other one is kind of one we don't think about breathing out a whole lot. We notice it though when it's cold outside in the winter. We walk outside of our house or whatever, and we breathe and we can see our breath. Do you know what it is that you see when you see your breath on a cold day? Or maybe think about it this way. If you go up to a mirror or a window and go, what happens to that mirror or window? Like it's fogged up, right? What is on that mirror or window now? Well, it's water. You're breathing out water. So our reactants, the things that go into this chemical reaction, are wax from the candle and oxygen from the air. The things that come out of the reaction are carbon dioxide, just like when we breathe, and water, just like when we breathe. Okay? So I'm going to put the candle out and we're going to write that down. I put a squiggly line here to indicate a separation of ideas. And next I wrote down candle reaction because that was the next thing that we needed to talk about. And I want you to write down wax plus oxygen becomes carbon dioxide plus water. And next we're going to look at this a little bit more, but I want you to write down real quick the law of conservation of mass. I also put law of conservation of matter is another thing you'll hear it called I tend to call it the law of conservation of mass, but it's the same thing. The law of conservation of mass says that matter cannot be created or destroyed, only changed. Whatever atoms go into a chemical reaction must come out. Okay? So like I said, pause if you need to, get that written down. What I'm going to do is we need to take this candle reaction written in words and actually put it into chemical formulas. So what we're going to use for wax, let's make sure this is nicely visible, is CH4. Now, I do want this kind of to be all the way across my page, and I'm going to give myself lots of space because we're actually going to fill some numbers. We're going to fill some things in here. So you'll see that I've spaced things out quite a bit. You should space them out too. So CH4, capital C, capital H, and a little subscript 4. Plus, it looks like a T, plus the oxygen we have in our air is capital O, lowercase, not lowercase, subscript 2, O2 is what we call it. And then that becomes carbon dioxide, which is CO2, capital C, capital O, subscript 2, plus, hopefully you know that water is H2O. Okay, capital H, subscript 2, capital O. So there's kind of our chemical formula. Now, what I'm going to do is illustrate these molecules with these little paper circles. So this one is CH4. The C's I'm representing with black circles. The H's I'm representing with white circles. And then you'll see here's an O2. The O's are represented with red circles. Okay. If you have colors, great, you can use them. If you don't have colors, what you can do instead is just do like a solid circle, a blank circle, and a striped circle or something like that. We only need those 3 kind of colors or forms. So there's our CH4, our O2, and here's what CO2 looks like. And it dropped some of them. Here's an H2O. So go ahead and write that down in your notebook. Try to make sure that they're kind of lined up. So we've got our CH4, O2, CO2, and H2O. Go ahead and write that down and come back when you're ready. Okay, now here's the thing. This reaction is not quite right just yet. We need to balance it. This isn't following the law of conservation of mass. Okay, so the law of conservation of mass says that whatever comes into a reaction has to go out of the reaction. So basically, the numbers of the different types of atoms need to be the same on each side of my pencil. I put this pencil here underneath the arrow so that I can separate the reactants from the products. So there we go. So what we need to look for is to be sure that, for instance, the number of black dots are the same on each side. In this case, they are. Let's look at the red dots next. Are the number of red dots the same on each side of the arrow? Or, yeah, on each side of the arrow or each side of the pencil? No, we've got 2 of them over here and 3 of them over here, so they're not equal. Same thing, the number of white dots, or H's, are unbalanced. I've got 4 of them over here and only 2 over here. So we need to balance that out because this is breaking scientific laws. This is not physically possible. So what we need to do is balance it out. And the way we can balance it is by adding another H2O and adding another O2. Now if we count up our numbers of different colored dots, now we've still got our 1 black on each side, but now we've got 4 red on this side and 4 red on this side. We've also got 4 white over here on the left and 4 white over here on the right. So this is balanced. This is good. This obeys the law of conservation of mass now. Now the final thing we need to do here, now that our equation is balanced, is we need to represent that up here in the equation. Okay, so what I'm going to do is I'm going to take a different color just so it stands out. You can use the same color. And think of this like a recipe. Sometimes with a recipe, again, say we're making a cake, maybe you'll need, I'm going to move this paper, maybe you'll need, 2 cups of flour and only a half a cup of milk, right? So we essentially will say, well, for this reaction to happen, we just need 1 CH4. So I'm just going to leave that listed that way. But I need 2 O2s. So I'm going to put a big 2 in front of the O2 to indicate that I need 2 of those. This CO2, we only need 1 of them, so I'm going to leave it alone. But I need 2 H2Os in order to balance this. So I'm going to put a big 2 right there. Okay? So that is our final balanced chemical equation. This now obeys the law of conservation of mass. Do copy down this whole entire picture with those 2 extra molecules added to be sure that your picture in your notes is balanced. Now, I do want to show you one more thing, some vocab. The coefficients are the big numbers in front, like those big 2s that I just added. This is the same formula that we just looked at, CH4O2, CO2, H2O. The coefficients are what we call those big numbers in front. The coefficients, and this should go in your notes, the coefficients tell how many of a molecule is involved in a reaction. And the subscripts are the little numbers at the bottom. The subscripts tell us how many of an element is in a molecule. So 2 very important pieces of information there. Okay. So that was the end of our notes for the day. So good luck. Let me know if you have any questions.